All right, let's take a look at using the maximum distortion energy theory. So here, the shaft is supported by journal bearings at A and B that exert force components in the X and Z directions. If the allowable normal stress for the shaft is 15 ksi, determine the smallest diameter of the shaft to the nearest 1/8 inch. All right, so what I'm going to do is I'm going to do it very similar. I'm going to find reactions, find the shear and moment diagrams. Then we're going to use the equations, but I have a programmable code that I use, and I'll show you that. Okay, so let's go ahead. We can just go ahead and do the problem right from start. So given we got sigma allow is 15 ksi. We're looking for D. We're going to use the maximum distortion energy theory. Okay. We got our sketch right there. And let's get right to the solution. Okay. We're going to find reactions. Let's look over here. This will be the X, Y. This is the points on here. I'll label C, A, D, E, and B. And what we have is 200 going down, okay, because we're looking at the XY plane. Let me go up. This would be AX. This would be 250. And then we have BX. Okay. I'll do the other side here, which is what? I'll do it like this. This is the ZY plane. Okay. We also have C, A, D, E, and B. And then in here, we have 50 going down, and then we have BZ here. Okay? Cool. So, again, sum the moments in the A, set it equal to 0. Up is positive. Okay? 250 times 16 inches minus BX times 20 inches plus 200 times 8 inches equals 0. You get BX to be 280 pounds. Oops. We can sum the forces in the Z, set that equal to 0. Not the Z, sorry, the X. We have minus 200 plus AX plus 250 minus BZ equals 0. We plug in, sorry, this should be BX. Plug in BX, and we get AX to be 230 pounds. And let me just fix my notes real quick. This is X and X. There. Okay. Over here, we are going to sum the moment again at A, set it equal to 0. This way is positive. We have BZ times 20 inches minus 50 times 8 inches equals 0. BZ becomes 20 pounds. Oh, and I forgot over here. Oops. This is AZ. Sorry about that. Then we can sum the forces in the Z, set it equal to 0. Up is positive. We have AZ minus 50 plus BZ equals 0. Plug in BZ, and you get this to be 30 pounds. So let me write all this in. This is 230, 280, 30, and 20. So again, Draw your free body diagrams in two 2D dimensions. Find your reactions, and what we're going to do now is the shear and moment diagrams. So let's do the shear together, okay? And I'll do dotted lines. So this is going to be shear, shear, pounds, pounds. So we're looking at the YZ. So it goes down 200, right? Then it's going to go over. It's going to go up 230. So this right here is 30. This is minus 200. Then it's going to go all the way over to E. It's going to go up. Oops. And then over. This value here is 280. And then it's going to go back down. Let me fix that. This is our shear. Over here, it goes up at A, right? To 30. Goes over, goes down. Sorry, that's not linear. That's horizontal to negative 20. And then it goes all the way over and then up. And that's your shear over here. Cool. Keep going. Let's go ahead and do our moment. Okay. Down, over. And let me move this up to here. And I'll move this up a little bit too. Yeah, I can put it right there. Okay, we got moments now. Pound, inch. And moment, pound, inch. I'll do black here. All right, so this starts at 0. And it's going to go to A. I'm going to go all the way down to here. And this is going to be 1600, which is 200 times that dimension, which was what? 8 inches, right? So 200 times 8, 1600. Then it's going to go up like this. And then it's going to eventually go to 0 here. Okay. Now, it was positive. This distance here is 480, and that's 30 times 16, right? Because it's shearing at 30, and this dimension is 16. Okay. So that's why it actually, this is a negative 1600, right? So this would come up to right here, negative 1120. Okay. Now, I forgot a line over here, which is fine. We'll put it in now, because we need to know the moment there. We will. That point right there. I'll just go over. So right here, this is negative 1360. That's the moment at D. Okay. I believe we're going to use that to check some stuff. Okay. And again, you can just figure out that's 30 times whatever distance and then just add it to 1600. There's our moment diagram. Okay, now let's go over here. This moment diagram can start at 0. It's going to go up. This value is 240, right? That is 30 times the distance. Then it's going to go all the way to 0 at the end here, because that goes down to negative 20. And what we need to do is find this value here, which is actually 80. Okay, because this distance between these two is 160, which is 20 times 8. Okay, so it's this shearing times this distance, which is 8. Okay, so here is our moment diagrams. Boom. Now let's look at the torque, and I'm going to redraw it right here. Let's use black here. We have C, we have A, we have D, we have E, and we have B. So we have a torque here called TC, torque here called TD, and then a torque here, TE. We scroll up, right? This force is causing it to go that way, and that way. Okay? And we can find these torques by taking this force, multiplying it by the radius of those gears. So, TC is 200 pounds times 4 inches. You get 800 pound times inch. TD is 50 pounds times 4 inch. You get 200 pound inch. And then TE is 250 pounds times 4 inch is 1,000 pound per inch. So how does this look like? Well, let's go ahead and draw all these in. And I'll draw this over. It's going to start here. It's going to go down to negative 800. Because that's there. Then it's going to go over to here. And that's another 200. So it's going to go down. And then it's going to go over. And then up. This is negative 1,000. Okay, now that we have, right, the torque graph, let's go ahead and use the distortion energy theory and find our required diameter. Okay? So, distortion energy theory states that sigma 1 squared minus sigma 1 times sigma 2 plus sigma 2 squared equals sigma allow squared. Okay. Then we have sigma 1 comma 2 is going to be sigma over 2 plus or minus square root of sigma over 2 squared plus tau squared. Okay. Sigma 1 is your plus version, and sigma 2 is your negative version. And we're going to use sigma as mc over I, where I is equal to pi over 64 d to the fourth. And c is d over 2. So we can actually write sigma as m d over 2. This is pi over 64 d to the fourth. And we're going to write tau as tc over j, where j is pi over 32 d to the fourth. And again, c equals d over 2. We're assuming this is a solid shaft. So this becomes t times d over 2 over pi over 32 times d to the fourth. And we're going to use m as your maximum resultant moment, and t is the torque found at that location for the maximum moment. Okay, So let's see. The maximum moment should be found at A. Okay. So M A is going to be, what do we have? M A x squared plus M A z squared. All right. Because if you look at location D, yeah, that's 240. Let's do it. We'll do both. MA equals, this is 1600 negative squared plus, I believe this was 0. Yep, 0 squared. So MA or M is 1600. Now say we pick D, square root of negative 1360 squared plus, that was 240 squared. And let me check this on my calculator. Yeah, you get 1381. So this is the spot you want to do it at. Okay. And the torque then at A is 800. Okay. So what I ended up doing was a MATLAB or a programming code. It could be MATLAB, Octave, Python, but I have access to Octave. So let me scoot this down here. All right, so we have our sigma allow, 15K, our maximum moment, 1600, our torque, 800. And then I did a switch case just to show you, okay, we're using solid, so that's I, and that's J. And what I'm doing is I'm actually initially going to guess a diameter from 0 to 5, and I'm going to calculate everything. All right. So I'm going to calculate all of the sigma values, all the sigma 1, sigma 2, all the tau, and then I'm going to compare it to the sigma allow. So what does that mean? Well, if I go back up here, I'm using this equation right here. Okay. And I'm going to call everything in this left-hand side. And I'm going to compare it to sigma allow squared. All right. And I have basically like diameter, and then I have left-hand side, and then I have sigma allow, right, squared. I'm going to pick a bunch of diameters. I'm going to calculate a bunch of left-hand sides, and then this number is always going to be the same. And I'm going to figure out at which row they're the closest. And then I'm going to grab that diameter. Okay. So that's what I'm doing in here. So I picked a range of diameters, calculating my I's and J's, finding my sigma, my tau, finding then the left-hand side, right? And then I'm comparing it to sigma allow squared using this cool little code here. Okay, where I subtract them, find the absolute value, find the minimum, and this gives me what that minimum value is, and this tells me the location, or if you want to call it the row, where these matches, and you can then extrapolate or interpolate or whatever the diameter. Okay, then I'm rounding to the nearest eighth. So when I run this, I end up getting 1 1/8 for our diameter. For me, this is quicker than trying to algebraically solve this. This is just a quick numeric guess to get my answer. All right, so in summary, let's go back here. We used this energy distortion theory on this particular problem to find our smallest diameter. our smallest shaft diameter. So the process, again, is to find reactions, do a shear, do a moment, do a torque diagram, use your distortion energy theory, finding the maximum moment magnitude, finding the torque at that location, and then go ahead and plug and chug and see what you can find. All right, I hope this makes sense. If you have questions, let me know.